Okay, this is our first new idea. We're starting our new semester of calculus, and we are getting straight into it. We are moving from this idea of our slope at a specific point, and I'm going to end up bringing that back later, but for now we're moving away from that. And we're going to go to this idea that we've sort of touched on when we've used our eyeballs to approximate, and we're going to get more into the nitty-gritty of it, about this idea of area under the curve. And so I have the same function here, f of x equals x squared plus 1, but I'm going to do two things with it. So this first thing that we're going to think about is, how can I find the area under the curve of this function? We're going to start by looking at the left one. And I'm only going to go from 0 to 3. So I'm going to draw a red line here. We're looking at the area under the curve from 0 to 3. And I'm going to highlight it, or shade it blue. We're trying to find this area right here, this blue area. But how do we do that? How do we find this area under the curve? Because I don't know what to do with this. Well, let's think about things that we do know. Because that's really what math is taking things we do know and using it to build us up to something we don't know. So I don't know the area of this shape. But what are shapes that I do know the areas of? Well, the easiest shape, one of the first shapes you learn in elementary school, is a rectangle. So let's start with that simple idea, that fundamental shape of a rectangle. And let's think about what is the area under the curve if we make a bunch of rectangles. And I'm going to do 3 rectangles here. Why? I'm choosing 3 because it makes the math nice, not for any super specific reason. But now, I'm splitting my thing into 3 even rectangles, and the reason it makes it nice is because we have one of our rectangles here at 1, and one of our rectangles here at 2. And I haven't drawn the top of the rectangle yet. I'm going to wait a little bit on that because I just want us to do a little bit of a refresher. The area of a rectangle is equal to base times height. That shouldn't be a revolutionary idea there. And I haven't talked about the height yet. That's the part that I said I'm ignoring for now. But we can talk about this base. We can talk about the base of our rectangle. And it's also length times width, same thing. But here I think base makes more sense. The base of our rectangle, well, we have 3 rectangles. Let's start with this rectangle here. This rectangle right here, it has a base of 1. And really, all 3 of our rectangles have a base of 1. So let me actually make a little bit of labeling. Let's call this rectangle 1, rectangle 2, rectangle 3. And then our base for all 3 of these rectangles is going to be 1. So the area of all of our rectangles is 1 times our height. And the height is where things get tricky. So I could draw these rectangles a lot of different ways, and we're actually going to explore 4 different ways that we can, well, 3 different ways we can draw our rectangles. And then we're going to explore another shape completely as well. But for this part 1, what we're going to do is we are going to take, let's choose purple. I'm going to look at the left side of my rectangle, and that's going to end up being my height. So I'm going to draw a line from the left part. So at 0 all the way to 1. And that's going to make one rectangle. So we have this rectangle here, and then I'm going to go from my left to the right, so starting at the left border of rectangle 2 to the right. So from here to here, and we actually draw dots. I think that'll help visually. So from here to here, and then my third rectangle, again, still going from the left of my function, the left border of my function, here to here. And we're going from there to there. Okay. So now that we have these three rectangles really drawn, we know our base is 1 for each of these. And now what's the question of our height? Well, we started at the left side of this. So what is this value right here? Well, this is going to be our function value at 0. And then if we go here, it's going to be our function value at 1. And then we go here, and it's our function value at 2. So we have 3 rectangles. And I'm actually going to introduce us to some sort of fancy notation. So we know the area of our rectangle is 1. Let me actually I'll keep going because I've already gone too far. Okay. So I'm going to introduce us to the notation. This is called let me hold on one second. Okay, I just wanted to make sure I was getting my Greek alphabet right. This is a sigma right here. This weird looking E thing, that is a sigma. And when we see a sigma, it means sum. It means to add. And we're doing 3 rectangles. So we're going to go from let me get my notation right. I'm trying to choose the right letters here to set us up for success. I equals 1 to 3, because we're adding 3 things. So we're starting at 1 and we're going to 3. We're adding 3 things here. That's what this is saying. And we are adding our base times our height, which I'm going to call our height. We're going to replace that now with f. Let me just do one parentheses. F of x sub I. Because our base is the same for all of these. Our base is 1, and our function value is this 0, 1, and 2. So really, actually, let me shift my sigma over since... Well, no, it's fine. I don't have to do that. So x sub 1 is 0, x sub 2 is 1, x sub 3 is 2. That's a little bit confusing, but I think y'all get the gist. So I'm not going to worry about it. Okay, and now let's expand this sigma notation. My freshman will be having a field day with me using this Greek letter. Okay, so our base is 1 for all of these. So if we expand this, it's going to be 1 times f sub x1, which is f of 0. So I'm gonna not write out the full math, but f of 0, 0 squared plus 1 is just 1, plus, again, a base of 1 times, my thing is not updating like it's supposed to be. There we go. Okay, and then f of 1 is 2. And then plus 1 times f of 2 is 5. Okay. And so if we sort of just simplify this, that's going to give us 1 times 1 is 1, plus 1 times 2, that's 2, 1 plus 2 is 3, plus 5 is 8. So we get that this sort of area under the curve that we're approximating is going to be 8. Oh, let me also add one more thing to sort of make it clear. This is the area of rectangle 1, area of rectangle 2. And I'm really trying to take my time and make this neat. This is a lot slower than I really want to go in class. But, okay. So this is the area of all our rectangles. We're adding them together, and we get that 8 is our approximate area under the curve. So let's write that. Area under curve is, I'll just say about 8. Now, is this the true area? Can I say this area is equal to 8? No, of course not. Obviously, we're missing all this stuff up here, this stuff here, this stuff here. We're missing pieces about this. So with this Riemann sum, which is just adding the area of rectangles underneath, really, is this going to be an overestimate or an underestimate? Well, this is going to be an underestimate. And why? Well, I'm going to sort of give that to us here. We're going to say that I'm going to give us the name for this now. This thing that we just did where we start from the left, this is called a left-hand Riemann sum. Left-hand Riemann sum. And this, clearly in this case, it underestimates. I just messed up. Okay, here we go. Underestimates. And why is it underestimating? Well, it's underestimating because our function is increasing. So if we start on the left, we're going to have the lower side of our function. So it's underestimating because f is increasing. And if you sort of flip that around, you would also get that it overestimates when f is decreasing. And I will ask you questions about is our approximation an overestimate or an underestimate? Okay, so this is our left-hand Riemann sum. I'm going to do the same thing, except now I'm going to come over to this other one, and I'm going to skip a little bit of our notation. I'm going to come to this right one, this right picture. And if you remember back when we did limits, we had limits when we come from the left and limits when we come from the right. And now I'm doing a left-hand sum. Well, the next thing we're going to do is we're going to do a right-hand sum. So we're still looking at the area under this curve from 0 to 3. And I'm still going to do 3 rectangles just because it makes the math nice. So I'm sort of splitting it evenly. And we're only going to worry about even Riemann sums. I'm not going to worry about different ones. You don't have to worry about that. Because actually I'm going to talk about this. I'm going to come back to this base and add a piece to it when we get to our final notation for Riemann sums. So now, instead of going from the left, I'm going to go from the right. So what color did I use? I used purple. So instead of starting at 0, I'm going to start at 1, and I'm going to go to the right and draw my rectangle. Instead of starting at 2, instead of starting at 1, I'm going to start at 2 and draw my rectangle. And then instead of starting at 2, I'm going to start at 3 and draw my rectangle. And hopefully you can sort of see, oops, whatever, same, it doesn't matter, what's happening here in terms of overestimate and underestimate. But let's go ahead and calculate the area under this curve. And I'm just going to use my go ahead and use my proper notation. So we're still summing up 3 rectangles. So we're going from 1 to 3. And our base is still going to be 1, which really I could actually just write that as a 1, but I'm going to write it as b for now because it's going to become something else later. And then our height is going to be f of x sub I, where our f of x sub i's are now different. Our f of x sub i's are now going to be, we're looking at f of 1, f of 2, and f of 3. And I'm going to save you a little bit of time. I'm going to pause myself. If you want to go ahead and try and calculate this on your own, you can, but when I come back, I'm going to just have this sort of written out for you. So you can go ahead and pause the video and try and figure out the right-hand Riemann sum of this. Okay, so coming back, I got that the area was 17, the area under our curve. And again, what am I looking for? So the area under the curve is about 17. And again, we'll talk about overestimates and underestimates. Well, what is this called before I even say that? If my thing will cooperate with me. Okay, this is a right-hand Riemann sum. Right-hand Riemann sum, and hopefully just by looking at this you can tell that we are overestimating because now we have all this extra space here and this extra space here and this extra space here. So we are overestimating because f is increasing still. Or we would be underestimating because f is decreasing. And I'll let you sort of have some visual examples in class about what's happening there. All right, the last thing that I want to sort of talk about is how can we get this into nicer notation? And eventually the notation that we're going to get to, which is integration. Let's talk about our base of our rectangles. And I sort of skipped over this when I did it, but I'm going to come back and do it now more precisely. We were going from 0 to 3. Our bounds were 0 is less than x is less than 3. Less than or equal to in both cases, technically. And I said we're doing 3 rectangles. So how can I divide this space evenly? Well, I'm just going to take our whole thing, the whole x distance we're covering. So we're going from 0 to 3. This is a distance of 3. And I'm going to divide that by our number of rectangles, which was 3. And this, let me use this notation actually. This is going to give us our base, which our new fancy word for this, if you remember when we did derivatives, I also used this. This is going to be delta x. And in general, our delta x is going to be equal to our x distance divided by our number of rectangles. So we have our x distance. Maybe I should take that out in case that's a little confusing. It's our x distance. I don't need a dash there. Our x distance divided by our number of rectangles. Okay, and now let's come back to our sort of summation notation, and I'm going to give us our final piece for this. So moving to our sigma notation or summation notation, our general rule is we are going from I equals 1, or it could be k. You could have some other letter there, but I'm going to use I, to n, which is our number of rectangles, which could be 3, it could be 2, it could be something else. And we're multiplying, I'm going to sort of flip it here. Our function value, depending on if we want left or right, that'll change, times our delta x. And I'll give 2 sort of reasons why this delta x should be here. First off, if you were in college, if you take calculus, delta x will not always be the same for every rectangle. You have to do uneven Riemann sums. And the other piece is that delta x, actually I'll save this second piece as a thing we get to later. But now let's think about connecting this to a perfect approximation. So if we want a perfect approximation of our function, well, what are we going to be doing? Let's come over to our picture here. What are we going to be doing to our rectangles? I'm going to draw on this right one because I haven't drawn as much here. Well, let's say instead of 3 rectangles, I make it 6. We do 6 rectangles, and I'll keep it as a right-hand sum. I'll refresh it in a second. I'm just trying to get all my things together. Oops, I messed up. It's going from here to here. Let me choose a different color actually than purple. It's going to be confusing. I'm going to do this new color in white or whatever, or black. So I'm doing 6 rectangles now. And I think in class I'll have us do this as sort of an exercise. But I have my 6 rectangles, 1, 2, 3, 4, 5, 6. And something that I'm just going to immediately point out is if we look at our second one, look at all this space. I'll just highlight it yellow. This space all here all that yellow space is no longer part of our approximation. We just lost all that extra stuff. Well, let's try it again. Let's go again. This time, let me choose brown. Let me make it 12 rectangles now. So if I'm doing 12 rectangles, so I'm splitting it in half again. This is going to take me a little bit to draw. Let me refresh it so you can sort of see it a little bit quicker. Splitting my rectangles in half again. I said it was brown, but it's actually yellow. It's brown. It's brown on my screen, but it's yellow on y'all's. My colors are a little different because I have dark mode on my tablet. So that's why it doesn't always look the same to me as it looks to y'all. You see, do I need to split this one? I think I do. Yeah. Okay. And this next part, I'm going to highlight blue, but I think it'll turn green automatically. But you see now, again, if we look at our left side of our... Am I missing one? No, if we look at our left side... Oh, no, it's not going to turn. This stuff that's going to be blue, we've now taken out of our approximation. And so our estimates are getting closer and closer as the number of rectangles increases and increases. Well, we have a handy notation. What if we kept drawing more and more rectangles? I'm not going to keep doing that because that's going to take forever. But if we want our number of rectangles, which is n is our number of rectangles, to go to be as many as we possibly can, we're going further and we're making more and more and more and more. How many are we eventually going to end up making? Well, we're going to end up making infinite rectangles, but we can't actually go to infinity. But what we can do is we can say, let's take the limit as our number of rectangles approaches infinity of our summation. So let's go back to limits. An integral at heart is also a limit of f of x sub I times delta x and this piece right here is actually something that we have a really nice notation for, which I'm going to go ahead and give it to you now, but we're not going to explore it any further and apart from our Riemann sums. But this is actually our integral from a to b of f of x dx. And I said I would save it for a little bit later, and here's that little bit later. This delta x is our dx. When we do our derivatives, the derivative of y with respect to x, it means change in y over change in x, very small values. Our dx is something very, very small because we've done infinite rectangles, so our delta x is basically 0. It's not 0, but it's basically 0. And so that's why we use dx, because it's a number really, 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 really small. And this video has lasted a long time. The last sort of thing I want to say is I want to come back over to these two here, and I want to connect this to what would our Riemann sums look like in really formal notation, or using this integral notation. So our integral from 0 to 3 of f of x dx equals, and I'm going to make my other writing smaller because I'm running out of space. This is just going to be equal to the limit as x approaches, I'm sorry, not x, as n approaches infinity, of our summation from I equals 1 to n of f of x sub I. And I'm going to make our delta x really specific here. Our delta x is our x distance. What is our x distance? Our x distance is 3. Actually, I'm going to make the other part more specific as well. Is 3 divided by our number of rectangles. Well, our number of rectangles is n now, if we're being really fancy about it. So this is our first step in making this really nice. The next part is this f of x sub I. Let's change that to be specific to our function. So that f of x sub I, well, that's going to be let me check myself really quick. Okay, for our left Riemann, I don't know where that came from. For our left Riemann sum, well, this is our limit as n approaches infinity. Oh my god, I'm glad you can't see it, but I drew the ugliest sigma possible. I don't even know what I was drawing. I equals 1 to n. And then we have f of x sub I. Well, that's going to be x sub I squared plus 1. And that's all times 3 over n. And then we are going to rewrite this x sub I just in terms of I. So if we're doing our left Riemann sum, when I is 1, we want 0. So really all we have to put here is instead of x sub I, we want a 0. We start at 1. So let's just do I minus 1 squared. Oops, I made a small mistake before I refresh it. So if we look here, if I do I equals 1, well then I have 1 minus 1 squared plus 1, that's f of 0. If I do I equals 2, 2 minus 1, that's f of 1. 3 minus 1, that would be 2. So we're just rewriting this in a way that it'll get us to where we want it to be there. Okay, so that's that one. This is our integral from 0 to 3 of f of x dx. And if we were able to evaluate this limit, which I don't think we have the tools to quite yet, we'd be able to find the exact area under the curve. Last thing I'm going to do is we're going to write our right-hand Riemann sum, which I'll let you sort of try it out on your own. I'm not going to go through every single step like I did with the other one. But if you want to go ahead and pause the video here, you can try and write your right-hand Riemann sum from 0 to 3. Okay, and hopefully you're able to get at least to this part here on your own. I will talk us through the x sub I part again because I think that's the trickiest part here. But now we're doing our right-hand Riemann sum. We're looking at x sub I. Well, here, when I is 1, for our first rectangle, we want 1. And then for our second rectangle, we want 2. For our third rectangle, we want 3. So here, in this case, we actually can do this really nicely. It's just going to be I squared plus 1 times 3 over n. We don't have to change anything about our I. It makes perfect sense to just leave it at I squared plus 1. And this is our definite integral from 0 to 3 of f of x dx. And we're one step closer to being able to actually find the area under curves. All right, this is another long video, but I'm going to try to have all these done before the break ends for when we come back in the semester as reference materials for y'all. Oh, let me add one more thing. I'm going to pause the video here and then I'll come back and I'll dash this around and say that this is our right-hand Riemann sum. Okay, and now I'm done.